So, good afternoon, everyone. Again, welcome to this workshop. So, I'm Evan Fernandez. I'm a research assistant with FOSSEE IIT Bombay. So, in today's workshop, we will first just give you an overview of what exactly is OpenFOAM and CFD as a whole. Then we will go ahead with the installation session. How will you install WSL on your Windows system? And then we will go to how to install OpenFOAM 9 and OpenFOAM 2412. I'll show you how to make an alias also so you can switch between both the versions. So you don't have to necessarily always open one of those versions. Once that is done, we will go ahead with the demonstration. In this demonstration, we set up 5 cases from each domain. So you'll have one from aerodynamics, one from heat transfer, one from multi-phase, one from turbulence modeling, and the last one from dynamic meshing. So stay tuned. We'll go ahead slowly by in this whole workshop. So the very first thing in CFD. So what exactly is CFD? As you know that it stands for computational fluid dynamics. In this, we solve some numerical methods using a computer algorithm to analyze some flow in very simple terms. So our numerical methods are mostly the Navier-Stokes equation for your normal flow simulations. So in this, we solve those equations iteration by iteration to get a desired outcome. So that is the main idea of CFD. And most of you may know CFD. You have it in your course as well. So you are introduced to it. So I will not go too much into detail. So we also know some of the applications of CFD. You have it in basically you'll have it in aerospace engineering. You'll have it in a mechanical field that is in your heat transfer. You will also have it in the space sector that is for your re-entry vehicles and all of those things. So before you make any product, you want to basically visualize it. How will it behave in a controlled environment? So through CFD, you can mostly predict how it will be before the actual product is pushed into production. So moving on to the next thing that is OpenFOAM. So what is OpenFOAM, you might ask? So OpenFOAM stands for Open Field Operation and Manipulation. That's the very basic full form of it. It was developed by Henry Weller in the 1980s and it's still being developed. Previously, it was basically you'll have two versions of OpenFOAM now. You'll have a .org version, that is the foundation version, and then you'll have the ESI version. The ESI version is the more up-to-date one. You'll have every six months some updates coming out, and you'll have new features in that. That's why we are going ahead with OpenFOAM 9, that is the ORG version, and with 2412, that is the ESI version. So OpenFOAM is a free and open source software that you have. Unlike ANSYS, if you've used ANSYS for any of your simulation, I think during your coursework, you will have been introduced to ANSYS because ANSYS is the more commercial variant of doing CFD. But again, once you graduate, you don't have those privileges. So you have to go ahead with something that you can use. So OpenFOAM is the very existence of that. So you have OpenFOAM to basically it's since it's free and open source, you can do most of your simulations and everything that you can do in ANSYS, but here it is free of cost. You have multiple options as well. Unlike ANSYS, you are restricted to a very select solvers. And if you have to modify something, you don't really know in the backend code. But in OpenFOAM, you do have that privilege. You can modify the solvers based on your application. So suppose I have a heat transfer case and I want to introduce, say, another factor into it. I can open the backend code, modify that, and create my own solver. So those privileges are there in OpenFOAM. And it also basically, if you're starting off with CFD and you want to learn the physics behind CFD, not just clicking buttons. So OpenFOAM is good that way because it helps you understand what boundary conditions you're putting. You're not just simply clicking a button and not knowing what it does. In OpenFOAM, the person who's using that software has to know inside out what exactly they're doing. Otherwise, you will end up with just as Professor Chandan would say, colorful fluid dynamics. Yeah. So the process of CFD. So this is a very basic flow of how you go ahead with a problem. So first you have your problem definition. Once you have defined your problem, what you want to simulate, you go on to the geometry and meshing. In this, you will create your domain and everything in it. Once you've done that, you will move on to the solver selection. What exactly you want to solve in that whole domain. So if you want for fluid, you will basically select a solver that is most relevant for it. If you want heat transfer, you will have some additional parameters. So you will always select a solver for that. Once you've done that, you will set up your boundary conditions and then you will move on to the solution. You'll check whether your solution has converged. Once you are happy with your solution, you can go ahead with the post processing. Now, these are some of the problems that you face. It's not always a straight line. Sometimes you will reach till the solution phase and then you'll realize that something is not correct. So there are multiple reasons for those. First can be either your geometry and mesh. So you have to go back to your geometry, tweak a bit, change some parameters, and then go ahead with the same process again. If still it is not up to the mark, then you will go back to the solver. You'll check whether that is set. You'll check your boundary conditions, whether those are set properly. So it's a back and forth process. If nothing is that simple in CFD, so you have to keep that mindset and you have to be a little bit patient. So in OpenFOAM, this is a typical case structure that you will have. Okay. So the very first you will have is a zero folder. In that zero folder, you will have your initial boundary conditions. This is where you will set your velocity boundary conditions, pressure boundary conditions. If you have temperature, then you'll set your temperature boundary conditions, and so on and so forth. Then you will have your constant parameters. Now, in your constant folder, you will have everything that remains constant throughout your simulation. So those can be the turbulence parameters that you have set, whether you're going to run a laminar or a turbulent case. Then you have your transport properties. Those can be the fluid properties that you have, since they will not be changing during your simulation. If you have some buoyancy effects, so you'll have gravitational parameters as well. So those will also remain constant. So all those things you will set it in your constant folder. Then lastly, you have your system folder. This is where you'll have all your simulation parameters along with your mesh. So the block mesh dict will create your mesh. You'll basically make base mesh if you're using SnappyHex. So yeah, your meshing is done with block mesh itself. You'll have then your control dict. This is where you will set your start time, end time, your delta t that you want to set. And additionally, if you want to set any functions, say I want to calculate force coefficients or any force, you'll see that in the demonstration sessions once we'll show that. So any of those post-processing utilities that you want to introduce, you will set it up in your control dict. And then you have your FE schemes and FE solutions. These are where you will change your relaxation parameters. If you have to introduce any of the algorithms or you want to change any algorithm, if you want to implement your custom algorithms, you can always put those into these files. Okay. So this was just an overview of how your case structure should look. Now, so we can start off with the installation session.